So this is kind of like, here's one of those neodymium magnets, pretty strong. One side is like north, one side is south. This is a representation of the field lines, the magnetic field lines, coming from that magnet. That, let's say this is north up here, and those field lines sort of start on the magnet and go around and end on the magnet. Okay? And so you could say, well, what's the field strength close to the magnet? You could get so many Tesla or so many Gauss. But it's not enough just to say, well, what the field is at this point. If you'd like to use this to generate a current, you have to basically cut these lines of magnetic force, these flux lines. And so it's actually, not only is the field itself important, but the direction of the field is important. So for instance, if you took, let's say, a loop of wire, and you move this loop of wire in like this, you're not really cutting any of the lines of force, any of the magnetic field lines. So you wouldn't be generating anything on this current, on this loop. It would just sort of go in and nothing would happen. But if you turn this, so it's like sideways, and then you started moving this thing, then you do start cutting lines of flux. And then you actually do start to generate a current on something like this. So you have to be, it's important that the lines of flux be perpendicular to the area, to the current that you're working with. And that is that okay? And that is kind of what we use by defining magnetic flux and magnetic flux linkage. That the magnetic flux is basically what these lines are. It's kind of lines of magnetic field going through space. The magnetic flux is, well, how much of that is actually going through an area, a specific area. And so you could multiply the field strength, which would be so many Tesla, times the area of the current loop that you're looking at. And that would give you part of it. But you have to take into account the fact that of the orientation of this. So for instance, if we're looking just above the surface of the magnet and all these flux lines are going straight up, then if we put this loop right around that, then we could say, well, how much flux goes through there? Well, then it would be, they're all perpendicular going through this loop. So, so all we'd have to do is multiply the field in Tesla by the area of that loop. And we get so many Tesla meters, Tesla square meters. And that would give us the magnetic flux linkage going through this little circuit. Now, if this was tilted in some way, then we still have the same area, we still have the same magnetic field strength, the same Tesla, but we've changed the orientation. So, and in this case, it would be like 0. So we have to take that angle into account by, we actually use a cosine term. So this magnetic flux linkage is the magnetic field strength times the area times the cosine of the angle between the perpendicular of this loop and the directions of the magnetic field. So if the perpendicular here is like straight up, so that right here it would be the same, it would be like the cosine of 0 degrees would be 1, but if it's like this angle would be perpendicular to it, it would be 90 degrees, the cosine of 90 degrees is 0, so it would have no magnetic flux linkage. And so that's where this that angle comes in. It really has to do with how well does this field, does this current loop actually cut or be perpendicular to the lines of magnetic field. Okay? So very difficult to describe that without something to show people. So that's, and if you use Tesla, you get like Tesla meters squared as a unit. Instead of Tesla, if it were Webers per meter squared, then Webers per meter squared times an area, which would be meters squared, actually comes up with Webers. And it turns out Webers is just a unit of magnetic flux. So it's basically how many lines you have. And if you have a large area that you're going over, then they're sort of spread out. And you have a very weak field, or if it's very concentrated, you can have a very strong field. And you can actually calculate how much magnetic flux goes through this. And if you had a loop wire radius 0.32 meters, a little bit higher than I have, and it's going through a uniform magnetic field of 0.8 Teslas, so something like this, where it would be perpendicular to the area, then you just multiply the field strength by the area, and you get something like 0.257 Tesla meters squared. But if this thing were oriented at like 30 degrees to the field, then you'd have a cosine 30 degrees in there, so it would bring it down to like 0.223 Tesla meters squared. And if you had like several loops, let's say you had a current here going through 6 loops, you'd actually multiply this by n, by the number of loops. So this is actually how you can build up magnetic flux in an area. You can put lots and lots of current loops there. And that's actually Faraday's law, is that the electromotive force, the voltage that we build up on this, is proportional to the negative of the change in lines of flux per the rate of the flux per time. So if you had a current loop here, and you had like 6 lines of flux, and then every second you took a line of flux out, if you're going through a lesser field, then you could say, well, I'm losing, let's say, 1 Tesla meters squared per second. Then that would say that you'd be getting a volt per second. So if you're losing like 1 Tesla per second, that would be basically 1 volt. And if you had several loops, let's say you had like 6 voltage, and it's the negative of the change in flux. So that if you're putting more flux in, you're actually getting like a negative voltage. A negative voltage being supplied. And actually, that sort of leads to Lenz's law. And these aren't Lenz's. What Lenz's law says is that if you have a current loop and the flux starts to change, the current in the loop will act as to oppose that change. So for instance, if that example that I'm taking flux lines out of here, so the flux is getting less, then let's say that this is north, so the lines are going north, and so the field strength is actually decreasing. So the field strength is getting less and less going north, going up. The field around this loop will then act to try and make that field stronger. So actually, using the right-hand rule, it will act to try and get a stronger field in the upwards direction. So the direction of current in here will be counterclockwise. Or if we were sort of putting flux lines into here, so it's getting stronger, it's getting a stronger magnetic field, then it actually acts to try and reduce it. And so the current would actually flow the other way. And this leads to interesting things, like this takes about maybe 10th of a second to drop, but through a copper tube, and what's going on there is that the magnetic field inside, well, this is a neodymium magnet. This is the current through this copper tube is acting to oppose the magnetic field. And so it's actually giving a magnetic field in the upwards direction that essentially slows that down. And that's it, gentlemen. Thank you. Thank you. You've been a wonderful audience.